Next up is Antti from Elisa, who's going to talk about building peering automation off PeeringDB. Over to you.
Okay, thank you. Hello everyone, my name is Antti from Elisa, and I will tell you about how we are using PeeringDB for automating our public peering configuration. And this is not about holistic automation, but rather a very low-level practical example how PeeringDB can be used to automate peerings. I think it's pretty easy to agree that time spent for manually configuring peering is time not very well spent, and it results in inconsistent configurations and so on. But it's not only about the initial configuration, but there are also things that tend to change during the course of time, most notably peer-specific prefix limits that are almost impossible to keep up to date by hand. But also things like peer descriptions that at first glance might sound like a very highly cosmetical thing. But I think that at an operational level, having the peer descriptions to reflect the real company names and network names is actually quite crucial. So, for example, like Elisa is no more called EUNET or Saunalahti, and the same applies to a lot of other networks too, because networks change their names and companies come and go. So this is one thing that is very useful to have automated. And regarding automation in general, I think that automation is best applied to big, bulky mass. And I think that peering configs is just that, and there's a lot of gain if you can automate and offload that from manual configuration. And also related to peering, there are things like your PGP policy frameworks and things like that that are very useful to be able to design only once and then repeat it. Actually, I stole that sentence from Jaakko's abstract. Thank you and sorry for that. About our peering automation, we migrated our international backbone, AS6667, IX peerings to an Ansible-generated configs last year. AS6667 is the network where basically all our peering footprint is. The domestic side, AS719, is likely to follow later, and same applies also to private peerings. And during the migration, luckily, most of the networks have their PeeringDB entries up to date. And for those that didn't have, some of those were directly contacted. Some of them were lost in transit. So the implication of this migration is that whoever wants to peer it, AS6667, needs to have their PeeringDB entries up to date, because otherwise the configuration will be not generated. The automation tool itself is pretty simple, just an Ansible playbook with a Jinja2 template that is rendered upon runtime using PeeringDB as a source of truth. This is not fully automatic, actually, but rather triggered by human intervention. So in this sense, it's only semi-automatic. But we do have this automatically rendering all the configs in the background via GitHub Actions. So all the full rendered configs are available all the time and updated a couple of times per day. We do have some initial plans to fully deploy automated config push to the network, but it still needs some work and quite some validation and checks before we can deploy that. This is how an IX looks in the Ansible YAML definitions. This is very simple. Basically, all we need is just to give some short friendly name for each IX. It's used in all the generated configs. It doesn't have any other meaning. And then one of the most important thing is an IX specific PeeringDB ID that links the specific IX to the correct PeeringDB entry. Then we have the connected routers are defined as a list, and a list is used because it might be, and there are situations where we have multiple routers connected to the same peering LAN, although in most cases there's only one router per LAN. And finally, the list of peers are defined as a list, or more specifically as a list of dictionaries. It's basically just a white list of all the peers in the given X that we are willing to peer with. The reason why the peers are defined as a dictionary is that this way we can define some additional attributes, most notably MDV's passwords that are currently defined this way. It's not very beautiful, but it's working. And we haven't had time and effort to over-engineer this because, after all, peers with MD5 passwords are a minority. So this is currently kind of a minimum viable working solution. We also have a possibility, technically, to define a keyword all for given IX. If we were non-selective, we could define that we are willing to pair with each and everyone in this given X. So it's a kind of catch-all whitelist. Okay, next I will present a few of the most relevant PeeringDB objects that we are using in this exercise. PeeringDB has a lot of different objects accessible via the API, but these objects are the most relevant for this our tooling. First of all, a net object represents each individual network, like AS66, 67, and IX object is the internet exchange, naturally, but it's actually the IX from the, how to say, from administrative point of view. It defines things like IX web page address, maybe some contact information and things like that. But the IX LAN object is actually the object that covers all the interesting technical data regarding given IX. And there seem to be such that there's one-to-one mapping between IX LAN and IX objects. For example, IX is like NetNode or some other where there are multiple different peering LANs. There are actually also, they are their own IX objects, so that each LAN have their own IX object, and as such their IDs are equal. I'm not sure if this is universally true, but I'm happy to stand corrected if this is not the case. And finally, NetIX LAN is the most important object in at least in our automation framework. This is the object that is kind of logical glue between a network and the IX. So each network is basically connected to an IX via net IXLAN object. This slide only has some screenshots to illustrate the different PeeringDB objects and how they are related to each other. I'm not spending much time to go through this, but these slides are available, so if you are willing to, you can look into this in more detail, and the API calls are also visible there, so feel free to experiment yourself. And about the Ansible playbook, it works in a way that whenever we run the playbook against single router or potentially against multiple routers at a time, per router we initiate PeeringDB API queries, and it works in a way that for each single router we first determine the list of all IXPs that the given router is connected to. So we pack all the IXs for that given router to a single list, and then we feed that list to the uppermost green dashed square to an API query that gets all net IXLAN objects for those IXs. So basically we get a list of all potential peers for a given router. And on the second Ansible task, we feed that previously retrieved list to a new query and get the respective net objects from the PeeringDB. This latter is basically used only for getting information like peer ASN name and so on. So those net IXLAN objects are basically the most important ones. Finally, when we feed this data into the Ansible template and render it, the generated config looks like this. The parameters that are highlighted are those that are received from PeeringDB, so those are the dynamic ones. All other stuff are more or less built into the template. This doesn't look like a rocket science, but when you multiply this tens or hundreds or maybe even thousands times per IX, there's quite a lot of gain in a way that a few lines of YAML definitions can result in a lot of configuration lines. And of course, this applies both to IPv4 and IPv6. No difference in those. Okay, then a couple of words about PeeringDB prefix limits. This is not strictly related to our template, but during the course of our migration, we have seen quite interesting numbers in PeeringDB max prefix numbers. By definition, the max prefixes in PeeringDB should be the suggested max prefix setting for each network, and at least I think that it should reflect the order of magnitude for the amount of announced prefixes, meaning that if you are announcing one single prefix, I think it is recommended to have max prefixes higher than one, because the moment you get the second prefix, I think you are not willing to lose your session. And that's why our template works in a way that if the PeeringDB defined value is less than 10, we round it to the minimum of 10. So 10 is always the minimum value in our generated configurations. Further, if there are networks that don't have max prefixes defined at all in PeeringDB, we are currently using a hard-coded default value of 1000. It's not actually a very good value, but the reason for this is that when we did the migration, we wanted to have kind of fail-safe value in order to avoid too many false positives, and that's why it has been 1000 since. And actually, I just had a look. It seems that there are only few, or at least minority of all our peers, that do not have max prefixes in PeeringDB. So fortunately, almost all do have some, at least some value. About PeeringDB API throttling, the PeeringDB API is quite heavily rate limited, even when authenticated. The rate limit is, as far as I know, is 40 queries per minute. It's not actually very much, because if you have hundreds of peers and you do a single query for each peer, you are quickly going to hit the rate limit. And that's one of the reasons why we are, like I previously demonstrated, why we are trying to pack as much as information into a single query as possible. But generally, to circumvent this rate limit issue, there are a couple of viable solutions. I think the best solution is to have, at least if this is done in volumes, is to have a local mirrored cache. There are publicly available tools to do that, so that you basically fetch the PeeringDB database into your own infra, and then you can use that as a target for your queries without any rate limits. We don't have that. We, as I said, we instead try to pack as many queries into a single query as possible, and it has been working for us. And of course, you can try to split your workflow into multiple smaller batches and maybe introduce some artificial pause in between in order to avoid the rate limit. But this is something that one needs to be aware if you are using PeeringDB as a source of truth. I will go back just because I forgot to specifically mention, but you see in these Ansible tasks that the API call is constructed in a way that there is we are not querying single IX ID or single net ID, but instead list of IDs, so that we can get as much information from a single query as possible. Then a few words about route servers. Route servers in this context are out of the scope, and they have been excluded from our automation. So this Ansible automation does not touch route server peerings at all. After all, route servers have entirely different configuration. They have their own PGP community-based policy framework and so on. So I consider that those are entirely different beasts. And on the other hand, I think there is some kind of chicken and egg problem, because if one is exclusively peering with route servers, one might argue that there's not that much need to automate bilateral peerings. But on the other hand, if you automate all the bilateral peerings, you might not have that much intent to peer with route servers. So this is kind of a chicken and egg problem. But in real life, I think there's some sort of hybrid approach that is usually followed. This automation framework is not complete and far from perfect, and there's still a lot of room for improvement. After all, this tool of ours only automates the configurations, but big part of the peering business and interaction is the communication with the peering partners, and this doesn't help in that at all. So I think this is something that if this could be at least semi-automated, it would help a lot. And one thing is also managing those currently used MD5 passwords. The presented solution is kind of a duct tape solution, but workable or works now. But in the long run, I think some kind of better password management solution is needed, especially if we ever migrate to authentication option instead of MD5. So this is something that needs to be worked out. And we also do not have very good feedback loop from the operational level, in a way that whatever we configure on the routers, there's not very good feedback loop whether or not the peering is actually established or not. So this Ansible tool only cares about generating the configuration, but what's happening on the network is not directly visible to the automation framework. And finally, it would be very useful to couple IRR-based prefix and maybe AS path filtering or both with this other automated config template. That seems to be my last slide. I think we are plenty ahead of schedule. So if we have any comments or questions or whatever, feel free.
Are you staying for the sauna?
I knew that you would be asking that. I'm unfortunately not joining sauna.
Are you staying for dinner?
Yes, yes.
Any quick questions for just now?
Excuse me, I just want to know that if...
Can you say who you are for the...
my name is Amin, from by the affiliation of Rionel. And I just want to know that if, could you test the, mix the Ansible with the a framework, like a robot framework, in order to, as an orchestrator to run the Ansible playbook, in order to say that it is a fully, automated solution or not. Just interesting to know that if you tested before.
Yes, I think it should be tested. We haven't done it yet, but this is more of a baby step forward. And I think that is something that, but we actually, in our company, we have a more comprehensive automation solution, and it's not tool like that. But I think in the long run, some kind of integration into our own self-made orchestration tool is the way to go.
Thank you. Thank you very much.
Any more questions for just now? Thank you, Antti. Great talk.